the sense of responsibility when you're about to start giving a talk. So this morning Julia told you about what happens in suspensions of concentrated swimmers. And you saw that there are lots of instabilities, so it's easily imaginable that if you have, for example, passive tracers there, if you put some fluorescent molecules, you'd see quite efficient mixing. And this is indeed the case, and there were a number of papers about that. And what is also quite interesting is that even when suspensions of swimmers are very dilute, you still have they still turn out to be effective mixers. And one of the reasons for that is that possibly they needed it in order to survive and in order to evolve, because clearly mixing increases fluxes of nutrients to them. And so in this talk, I'll be focused on very dilute limit, really, and the idea of this talk is to understand the fundamentals of this process. So here is an evidence that, on one hand, mixing, diffusion is enhanced by swimmers. So this plot comes from the lab of Ray Goldstein, and what you see is the probability distribution function of the tracer displacements for a fixed moment of time and for different concentrations of swimmers. So you see this thing, this parabola, which is essentially the Gaussian due to the Brownian motion. And you see that as the concentration of swimmers increases, so the width that's equivalent to the effective diffusivity in the system, the width of this curve increases as well. Also, what you see is that something interesting is going on here, because this distribution doesn't look like a parabola, and you clearly see fat tails developing. And that's, of course, something that cannot possibly happen in an equilibrium system. And one of the the question is what's going on in here, really. And on the other hand, when we talk about the questions of mixing, well, we can actually jump a few orders of magnitude up and think not about bacteria, but about something bigger. And because Len is in the audience, I couldn't resist but put this picture. So the question is, do small mixers mix the ocean? And that's really an ongoing debate and quite a controversial topic. So here's the names of a few people who contributed to this discussion. And if I'm not mistaken, Len's take on it was negative. No, they cannot, only if they are large enough. And they have to be quite large. But still, of course, here we're in quite a different regime. The Reynolds number is not 10 to the minus 5, minus 6, but of the order of 1, really, so that inertial effects become important. Still, I want to play this movie in order to see to show you that swimmers can actually entrain things behind them. So that's a nice picture giving an idea of what I will be meaning in the rest of the talk when I say entrainment, even though I'll be speaking about bacteria rather than these large objects. So the movie is really beautiful and rather self-explanatory. So this trail behind the jellyfish.
Reynolds number.
Well, it's quite large. I mean, quite large. It's not to the minus 6. It's 1 to 10, something like that. So it's quite reasonable to expect that inertial effects do play some role. Besides, you see traces here of some instabilities or some vortices. So don't take literally that this is exactly what happens with bacteria or sperm cells. No. So why do we study? Why do we want to understand something in this field? Well, on one hand, because steering, as I have already said, is a process that can be quite important biologically. And second is that it's from the physical viewpoint, it's an unsolved problem. So we don't have really a good understanding of how exactly mixing happens, what are the different mechanisms, what are their relative magnitudes. And besides, there is a number of tantalizing mysteries about it. For example, you can show that this process looks like anomalous diffusion on short time scales. However, if you go to larger time scales, it looks like Brownian. So the mean square displacement squares linearly with time. And besides that, there is an amazing dimensionality dependence on this process. So there were experiments done in the lab of Jerry Golub that showed that if you actually take the same suspension of swimmers, but look at the film of them under the microscope, then the effective diffusivity is increased orders of magnitudes. 100 it becomes from 100 to 1,000 times more really than it had been for a bulk system. And again, that's something really interesting and surprising. So the focus of my current talk is first, the focus of our research is comparison of different mixing mechanisms, and also discussion of the issue of universality. And by universality, I mean that it is not really sufficient to come up with a model of swimmers and show that it produces a sufficient increase in mixing, but you want to be sure that it's exactly what happens can happen in different systems, so that the details of this process should not depend upon the particular shape of the swimmers or upon their particular gait, because swimmers can actually choose different strategies for moving. Some of them clearly have flagella that, that are helical and propel themselves by pushing. And chlamydomonas, for example, they're swimmers. They're really doing a breaststroke. So their strategies are different. So the question is, how universal are the mechanisms that we discuss? And let's start with imagining a cell swimming in a straight line. This cell is moving straight, and it's neutrally buoyant. So that's we in the far field of this cell, we can pick a tracer particle and see how it evolves. And what can be shown is that actually these passive tracers in the far field of a swimmer move in closed loops. So they really start from the place where they finish in the place where they started from. And although the shape of these loops can be a bit different. And it's sort of intuitively you can kind of understand why this thing happens. If you look at the velocity field, at the flow field of the, in this case, a typical pusher. So it's pushing fluid forward and draws it towards it on the sides. And so you can kind of imagine that this flow field is prone to creating loops. But the flow field of a swimmer, of a quadrupole, the swimmer, a force-free swimmer can be a dipole, but it can also be a quadrupole. Well, in certain situations, certain symmetries force swimmers to be quadrupolar. And in this case, it turns out that still passive tracers move in closed loops, even though the topology, even though the shape of those loops can be quite different. So it's kind of interesting what makes the tracer remember the position it started from.
A mathematician might call a theorem. In other words, you can prove that in generally for any point-sized dipole and quadrupole.
So what exactly is the question?
But
yes.
Whether you can prove that, but it's a
I will show you the
not
proof.
Just a simulation, but
right. I will show you the proof in a moment, and we'll show that was exactly well.
Assuming there's no real field, it's just the field of
right. Correct. In this limit, you can show that it's exactly the
for
case.
all multiple.
1 minute. Just yes. Yeah. Probably just should yes.
Right.
So before I come to this question, I just want to show another movie, really. So in this case, you have a suspension of chlamyds, and these are passive tracers. And you can see, if you look carefully, you can see actually a number of things. You can see that a number of them, let me catch it. Well, essentially, well, for example, this one. So it just made a loop that's almost closed. Of course, a loop cannot be exactly closed, because if it were, then there would be no mixing, there would be no steering in the system. So it's actually this degree of loop non-closedness that tells you how efficient they steer the fluid. And so the plan for the rest of my talk, first to discuss why they make loops, and to exactly pinpoint where this closed loop picture breaks down. Second, to discuss how much fluid they drag along as they swim, and this leads to the famous in fluid mechanics concept of Darwin drift. And then, so we develop certain theory here and apply it to the classical model of squirmers, a particular type of swimmers, and more realistic examples by doing numerical simulations. So, well, let's come to the sort of approach the question of loops. First, well, I start with the fundamental solution of the Stokes equation. Essentially, this is a Stokelet, and J is the Gaussian tensor. So U tells what is US, tells what is the velocity at the distance R if a singular unit force applied is in the direction K. And as a swimmer is force-free, then this term in the multipolar expansion, of course, vanishes. And the next order term for a swimmer is the dipole term. And so it can be written as a derivative in the direction of swimming of the Stokelet and multiplied by the strength of the swimmer. So if kappa, this kappa is greater than 0, then those are extensile swimmers or pushers. And for negative kappas, they're contractile swimmers. Note here that that in principle you can have other terms in the dipole expansion, but so in 3D this is a tensor of the second with two indices, really a symmetrical one. So you could have in principle 6 components, six dipole strengths. So in 2D, because we're looking at x-isometric situations, that still reduces to 2 dipole components, one in the direction of swimming and another in the direction perpendicular to the swimming. However, only this component is present for for real swimmers, and this has been confirmed in experiments in Ray's lab. And the reason for that is in fact very simple. It's that the resultant of the drag forces and of the propulsive forces, they have to be aligned with the direction of the swimmer. So it's very often that, well, that's the form of the dipole term. Now, similar kind of thinking leads to the expression for the quadrupolar terms. And so again here, this is really differentiating along the swimming direction, and that's taking the Laplacian perpendicular in the plane perpendicular to the swimming direction. So correspondingly, there are quadrupolar strengths Q parallel and Q perp. And one more thing that has to be mentioned at this point is that if kappa is non-zero, then there is a slight difference in the physical, in how well defined the Q perp and Q parallel are. So in this case, when kappa is not equal to 0, then Q parallel is not really a well-defined quantity, because by shifting the origin, you could actually make it an arbitrary number. So whatever your theory is, if you come up with a physical prediction, you have to make sure that Q parallel actually doesn't enter it. So that's sort of a interesting, that's sort of an expectation that we always have to keep in mind. So what's this is a rather standard stuff, but what is less obvious here is that in fact, even when you have the dipoles and the quadrupoles, the sum of them, for example, you still can write the velocity field of swimmers as a derivative in the swimming direction of a certain vector function u0. And this turns out to be important because this is exactly where the loop closedness is inbuilt, so to say. So, and the proof of it is rather simple. So, let me first take the Lagrangian derivative of u0. So, I'm looking at u0 at the position of a tracer. And clearly, it can change because of two things. One is that the swimmer is moving, and the other one that the tracer itself is being advected. So correspondingly, the full Lagrangian derivative consists of two parts. The first one is due to the motion of the swimmer, and the second is due to the entrainment of the tracer. And typically, the second term is, of course, much less than the first one, because the flow of the swimmer decays pretty fast. So if we can neglect the entrainment, in this case, the Lagrangian derivative is approximately equal to the Eulerian derivative. And what I have here to the right, on the right-hand side, if you forget this v, then by definition, it's the velocity field of the swimmer. So correspondingly, this thing is nothing but the speed of the swimmer, approximately, the velocity of the swimmer. So if we are to calculate the total tracer displacement, it's of course the integral from minus infinity to plus infinity. So I'm imagining this swimmer going from minus infinity to plus infinity in a straight line. And after integration, the integration can be is sort of full, and we come up with this expression. So so it really depends upon the value of the function u0 at infinity. So if the function u0 is 0 at infinity, in other words, if the interaction is short-ranged, then this expression is equal to 0. So that's what is really behind the fact that loops are necessarily closed. And so the assumptions that we've made here are first that we can neglect the entrainment so that the swimmer is sufficiently far from the tracer, and second that swimmers move in infinite straight paths. So correspondingly, when one of these assumptions is violated, it would produce non-closedness of loops and would give rise to a mechanism and to a mechanism of mixing. So one of them I just mentioned, so it's really what we call entrainment. The second mechanism, well, that's when this gradient form is not really valid, and there can be a number of situations for that. So, for example, it can happen for spinning sperm cells, but as long as we're interested in axisymmetric transport, that is not really important. Now, what is quite interesting that in 2Ds, well, interactions are quite different. So u0 doesn't go to this sort of potential function doesn't go to 0 at large distances. Instead, it grows as logarithm. So, in this case, the previous argument doesn't apply, and that's why we actually must expect a strong increase in the diffusivity in 2 dimensions. So we think that's a probable explanation of, the probable basic reason behind what happens in films, in mixing in films. But we haven't developed the theory yet. And one more mechanism is, of course, when swimmers don't move in infinite straight lines, but instead they run and tumble. And that's what happens with clammies, for example. And it raises a question that it may be one of the reasons why they're doing it, in fact. So they have this inbuilt mechanism of going straight for a while, for quite a while, and then abruptly turn at sharp angles.
Sorry to interrupt again. Is an example of fluid entrainment at the top right is an example of that Brownian motion of the tracer, getting it to move off the deterministic path that is assumed in the calculation?
Well, no. At this point we really neglect Brownian fluctuations.
But if you didn't, they
Yes.
wouldn't stay on the closed path, would they? Whatever happens.
That's right. But in this case, you could argue that eventually the diffusion coefficient, the total diffusion coefficient, would be just the sum of them, really, unless you have some very large locations where the trajectory is being stretched, so to say, the Lyapunov exponent is pretty high. The integrated one, but
go on chatting. But
yes, but I've done these estimates, and I can tell you that as a result, what you get is there is no such significant enhancement of diffusivity just due to Brownian motion.
There's recent work by Eric Loga that we'll talk about.
Well, so one way to understand how exactly entrainment happens in this system is to imagine, well, to apply the concept suggested a long time ago by Darwin. Well, that's Charles Darwin, and also Sir Charles Darwin, just like his grandfather. And his idea was to consider a material sheet. And, well, of course, he wasn't thinking about swimmers, but he thought of taking a body and seeing how this material sheet will deform if a body moves from minus infinity to plus infinity. And what he found, and that was quite surprising at that time, he considered inviscid situations, and he found that if you then later calculate what now is called the Darwin drift, that is the total amount of fluid entrained. So in this case, it's the total, well, this total volume around this curve. Then this volume is actually equal to, for a sphere, to 1/2 of the volume of the sphere, and this 1/2 is nothing but the added mass coefficient. But that's for inviscid flows. Now we're in the opposite limit. And what we first look at is the shape of this material sheet far from the swimmer. And the first thing we find is that it actually, well, it of course decays, but it decays as 1 over rho cube, where rho is the distance from the swimmer path. And also, well, this is a general feature of entrainment, is that close to the swimmer, the particles of the material sheet are entrained along the swimmer's motion, but farther from it, there is always a region of backflow, so to say. And so now this expression tells exactly how the asymptotic of the shape of the deformed material sheet. And besides the first term, there is the second term that contains the product of the swimmer quadrupolar moment and the dipole moment. And this product is different for pushers and pullers. So that's where the difference between pushers and pullers starts to play some role. Notice also that only Q perp enters this expression, as we discussed, should be expected. Well, this shape of the material sheet far from the swimmer is dictated by its far field, and therefore it is of course universal in the sense that it is the same for all swimmers that have the same far field. However, it's not true close to them, because the details of their near field can considerably change this shape. However, it turns out that the volume that is called the Darwin drift is always a finite quantity, and you can actually make an interesting prediction about it. Namely, you can show that you can decompose it in two parts, and it is equal. The first part is proportional to the quadrupolar moment far from the swimmer, and the second part, it of course has the same dimension of the swimmer's volume, and it has a pleasing physical interpretation as the sum of the swimmer's volume plus its wake volume. So even though we're in a very low Reynolds number limit, swimmers may actually still have wakes. And this is very clearly seen, for example, for the model of Squirmer, a particular model of swimming. And so there is a number of names associated with this concept and its application in fluid mechanics. And so in this case, we start with Darwin and finish with Len. And of course us at the end. We find that this decomposition is quite important because it distinguishes between the universal features and non-universal features. So, I mean, I meant to talk a bit about how we come to this result, but maybe I'll just skip this slide, and if anybody is interested, and we can discuss it a bit later. And just now we want to see how well this concept works for particular cases. For example, for the Squirmer model. So for the Squirmer model, essentially what you have a spherical body, and you prescribe a tangential velocity in the form of two first spherical harmonics. And so this constant B1 essentially sets the speed of Squirmer's swimming, and the constant B2 sets its dipole strength. And if you just numerically calculate the Darwin drift for the Squirmer, you'll find that it starts off with the value 0.5 in the units of the Squirmer volume, and stays at this value for a while, but then drastically departs from it and even changes sign. It actually becomes negative when beta is above 2, and beta is the dipole strength, or equivalently the ratio of B2 to B1. So now, using the previous results, we can easily understand what happens. In fact, the Darwin drift in this case consists of two parts. It can be written as 1/2 minus the volume of the wake of the Squirmer divided by this by the Squirmer's volume. And this expression for this model can be obtained analytically, and we essentially obtain an identical curve to this one. So this concept really works well for this standard model, and gives some understanding to what's happening physically.
It's the same for either sign.
Yes, it's the same for other sign. Yes. So now we move on to more realistic models. So in this case, we have a numerical model of Rhodobacter spheroides, and we solve the equations of fluid motion exactly. So this is a boundary elements method with no slip on the swimmer's surface, and the swimmer is of course force and torque free. And well, we can control all geometrical parameters of this swimmer, and also elasticity of the hook that connects the flagellum and the body of the swimmer is also taken into account. And what we do with it, we shoot it essentially at a material sheet and look at its displacement. And we do it as the swimmer moves from -1000 to 1000, and then take our results for this case and extrapolate to infinite swimmer paths. So, well, that's the deformation of the fluid flow induced by the swimmer. And actually, I have a better plot. And well, this curve tells what's the displacement as a function of rho, and the green points correspond to the far field region. So the dashed line is our prediction to what it should be, and there is no fitting here involved whatsoever. So we were sort of pretty happy with this agreement. And now we actually move to estimating what is the Darwin drift of such swimmer as a function of its parameters. And the base case that we consider is when it is twice as long as it is thick, and lambda is the non-dimensional, in non-dimensional units, the pitch of the helix, and L is its length, and A is its amplitude. So this is the base case. And what we find is that, well, we find Q perp by numerically integrating the forces on the surface of the swimmer, and we find this value, and we also find that there is no wake for this swimmer. So using our previously obtained expression, we obtain this estimate. So 6.1, that's the Darwin drift. And that's the value that we obtained from simulations, and so we're happy with quite happy with the agreement. Now we analyze what's the influence of the parameters of the swimmer on its Darwin drift. And we find that if the swimmer is actually twice as thick as it is long, in this case the Darwin drift changes dramatically. It becomes twice as large. And we were thinking that for some bacteria of this type, that's actually what you see. You see that, and that's sort of counterintuitive. What you see is that their shape is not elongated, but rather they look like a corkscrew. And this actually may be a reason for that. So this shape provides stronger mixing. And we can also see that in this range of parameters, the length of the flagellum doesn't really matter much for the Darwin's drift. However, if you change it really a lot, then it still can change, and it can change so much as to change its sign. So in the previous case, the Darwin drift was in fact negative, so meaning that more fluid was moving to the back rather than was being pushed to the front of the swimmer. And that's in fact where I'm about to finish. So in this picture, in the picture of entrainment, we think that we've gained good understanding of really what's happening. We understand what is the fundamental reason behind the loop closedness, and have come up with the way to analyze the drift that swimmers induce on the fluid. So, well, thank you very much.
Okay. Plenty of time for questions and discussion.
Okay. What I was thinking of when I was asking your the question earlier was the stuff that Luga has done recently with squirmers, but with unsteady. Well, I think it's Luga. Somebody anyway, unsteady squirmers. I think Julia's done something on unsteady swimmers as well. And if you've got clavidomonas or something beating unsteadily, the cell itself moves up and down. So even yes, what I saw, even if you've got somebody beating in a reciprocal way, so that it actually makes no individual progress at all itself, the motion of the particles combined with a bit of Brownian motion gives them a much bigger effective diffusivity than if it was just the Brownian motion with a steady or stationary. So emphasis on the, once you take time dependence of the locomotory mechanism into account, you will get better mixing as well. Sort of, I don't know how it interacts with what you've done.
Well, I see. Well, I haven't seen this publication. It's an interesting idea. It's not really very much surprising to me, but I can imagine that. Essentially, what we've done, we've considered the steady state, right? The sort of time averaged case, and the mechanism that you are describing, my intuition is that it can lead to some increase of effective diffusivity, but I would be very much surprised if the increase was really considerable. I mean, it was much more than what we get. I think it would be a value of approximately the same order of magnitude. And there is something I haven't told you because essentially my computer had a glitch and I was just not able to get the last version of my presentation. So using these ideas, we're able to come up with estimates for effective diffusivity. So what we find is that, yes, this is the effective diffusivity that's of the order of magnitude. It's the right agreement with what's observed in experiments. But this is just one mechanism, and this diffusivity turns out largely independent of the dipolar strength of the swimmers. So it does depend upon it, but relatively weakly. Now, when the swimmers are strong enough, and that means not quite too strong, then we can show that for dipolar swimmers in 3 dimensions, it's the random reorientations mechanism that is dominant. So for people who do not really know what I'm talking about, it's just another idea how to break this symmetry, well, loop symmetry, loop closedness. Essentially, the particle is moving along a loop and is about to finish it, but then this swimmer suddenly changes the direction, so it's not really able to come to the point where it came from. So we now understand that this should be the dominant mechanism in most situations when the swimmers are bipolar.
And of course,
so
swimmer interactions generates randomness.
Right. Yes.
Okay. I ask a naive question about the dipolar field. So you show the dipolar field and quadrupole field as gradients of the swimmer velocity. Is that right?
It's as gradients of the of this Stokeslet.
Right, which is a a Stokes slit which exists everywhere away from.
That's
the
all
source.
away from the boundaries.
Okay.
And we also look at...
So my question is, if you start getting to finite Reynolds number, then there's retardation effects. Does that also screw up the loop behavior? You'd have a retarded potential rather than
yes, but this actually
That'd be relevant.
goes to... yes.
because you're taking a far field.
Well,
where that's gonna be more
when you increase the Reynolds number, the inertial effects, of course, start to become important.
Yeah.
And actually, I think that was one of the main points of the paper that Len wrote with Lishansky in PRE. I think that was exactly the point. That
Yeah, well, this was actually a completely different subject, and mixing competed with turbulence, with oceanic turbulence, not with laminarity. So it is completely different thing. But what is really enhances very much the mixing is non-stationarity and more this ratchet effect. If you remember this picture of jellyfish, it moves this way much faster than another way, and this makes these vortices asymmetric in time.
so
This should and this shouldn't happen. Now the question is, when your bacterium, if it wants really to evolve in such a way as to have more food, maybe it would evolve. It would evolve to have some non-stationary.
well, it would have to move very fast. So probably 1,000 times faster, and that would be very hard for them. So in their world is a world of, I mean, very low Reynolds number. So for them, the fluid around is like a very viscous honey. So it's really, and as they're driven by molecular motors, there is a limit to how much force they can apply. So it wouldn't work because of that. But for bacteria.
So when I was listening, you reminded about the description of the run and tumble flow of the clammy. I was thinking about what kind of a random walk is this, and I was thinking if there's a distribution of lengths before the run and tumble occurs, then this couldn't be a normal diffusion type of random walk. So, it might be interesting to just actually find measurements of the distribution of how far these creatures move before they run and tumble, before they tumble. How far they run before they tumble. Because maybe, is that something that people are studying?
Well, yes, this subject is sort of is being studied, but what I didn't get is why would you expect that it would not be an ordinary sort of Gaussian random walk?
Because this is a setup for superdiffusion and subdiffusion. When you have
Right.
distribution of lengths of your steps.
Right, when the distribution of length is really very large, and well, essentially, if it would be if it were a power law distributed, right? So, but well, for as long as we talk about diffusion of swimmers due to this run and tumble motion. It turns out that that's pretty much a usual random walk, and simply because the distribution of but this is something that of course can be looked more carefully at. But as far as I know, the distribution is not wide enough, really. I think I saw some experimental data about it. On the other hand, if we talk about, we're here interested in mixing induced by this run and tumbles mixing of fluid, yes, in this case, it actually does lead to the interesting effects of the type you're talking about. Simply because if you think of one swimmer on a very short time scale, then because its velocity field is power law distributed, is a power law, then if you think about the probability of finding a particle away from it, it's also a power law. And therefore, the probability distribution function of particle displacements at short times is also a power law. And in this case, you get a kind of Levy-Flight story. And this story, however, changes if you take into account the run and tumbles, again, not in a non-trivial way. But it's something that we've just recently, we think, made a good progress in it, so we haven't announced it sort of yet.
Well, thank you for your answer. When I started asking this question, it occurred to me that I might be talking about something which is really well known. But this superdiffusion and subdiffusion stuff is an interesting topic, present topic also.
I wonder what happens if instead of having a dipole, you have a couplet.
And the couplet meaning, by the way, what is it?
It is a singularity in the vorticity. It's produced by
Right.
couple, an infinitesimal couple,
Yes.
instead of an infinitesimal dipole.
So if you just wanted to find the fluid motion which is generated by these swimmers, and just think of the combined motion, the swimmers and the fluid, and you wanted to make a description of that. Could you imagine putting the swimmers into the stress tensor for the fluid?
What Julia has done.
Right.
But inspired
No.
by
Yes.
by the flow field induced by elementary singular
Yes.
solution.
I don't
You're
know.
asking if you have a little.
I have to think about it.
Yeah.
I have to think about it. I don't know what it's talking about. No, I
Virus.
understand. Yes.
I mean,
Well, I understand.
the couplet wouldn't contribute to the actual, I mean, of an isolated individual, it wouldn't contribute to its displacement.
Yeah.
You
It
could combine
would-
it
it
with
would-
the dipole.
But when combined with other things, it would do something interesting for mixing in 3 dimensions. So,
That's open too.
oh, well, if it's perpendicular, yeah.
Question here?
Did you catch the relationship between the non-closeness of the loop that you mentioned and mixing? I mean, or diffusivity. So, I mean, I think if you want to calculate some diffusivity, you need some statistical, you need some randomness. And why is this? I mean, gap. What is the relationship between this non-closed and effective diffusivity?
So, in this case, well, first I think that I think you do understand the general argument, right? That if the loop is closed, there can be no diffusivity. So, but in this case, what?
If screamer it moves randomly, then
Yes.
so
So essentially,
the even closed group enhances
Right.
diffusivity somehow.
yes. So in this case, well, if this is a material sheet that we talk about, and there is a swimmer coming to it. So the material sheet deforms, and sort of there is a kind of a trail behind it. If you think now that this part of the volume is color, of different color than this one, so there would be this sort of trail behind it. Now, if another swimmer comes at another direction, for example here, well, same thing would happen again in the game. And as a result, this boundary will get smeared, and this is a diffusive sort of process. And in order to understand, to estimate what's the effective diffusivity, you can come up with a rather simple argument, for example, similar to what's done in the kinetic theory. So you can argue that the effective diffusivity in 3D is just 1/6 of the mean free path, I'll denote it by lambda here, times the velocity of the swimmer. But as I'm talking now, I'm transferring volume. So times the characteristic, it has to be multiplied by the characteristic volume transferred. So V, and of course, times the concentration of swimmers. So now the estimate I talked about is that, roughly speaking, if lambda it's this length, if we approximate it, it's typically of the order of the size of the swimmer times 8. And then this V, well, there are different ways of estimating it. One of them is to use it essentially to take the Darwin drift of the body. It can also be argued that in principle you have to consider not the whole volume of fluid, but only this one, the one that's displaced in the positive direction next to the swimmer. In this case, it will be a slightly different quantity. But whatever quantity you take, you can show that it's, roughly speaking, of the same order as the volume of the swimmer itself. So if you introduce a coefficient, this V divided by V0, the swimmer volume, then it's something of the order of 1. And the estimate for the effective diffusivity is then, well, some number of the order 1, n times V times a to the power 4. And this is actually the estimate. So if you take, for example, Chlamys, you can take that A is equal to 5 micrometers, and V on the average is around 100 microns per second. Then, well, take the typical concentrations that, for example, were used in the race experiments, and you get D pretty close to the one we observed, a bit lower than that on the lower side. And so we call this exact mechanism diffusivity induced by entrainment. In addition, you can show that the effect of random reorientations can be just added on top of this one. And therefore, you should expect larger values of D.
So we're coming close to 4, so maybe what we should do is if a further question discussion, then we can descend on people. But yeah, we will have coffee upstairs, and then something about the pub.
Yeah, so we started last week sort of a
Tradition last week.
tradition last week that Thursday in the late afternoon, 6:30-ish, we would go to some local pub. And so last week we went to one. Of course, we couldn't find the one where we wanted to go. That was at the river. So
even on the way there.
no, it was further. so
let's think about
even
you
would
find it.
even would you lead this
Well,
evening's excursion to the one that we wanted to go last week? So I would say 6:30 maybe.
Any idea where? Because I'm going to something else. Just that I could come. Like it goes to 6:30, and I could come.
Steven,
Do you know the name of the pub?
which one? Steven, what was the name?
The one which one? The one we wanted to go to was the Chop House, but we went to the Boat House pub instead.
Well, what's the plan for tomorrow?
Well, I guess people it depends whether people want to eat or drink.
I mean, I guess we tried this chop house. So.
There are 2 shop houses. Which one?
Or we walked past at least one.
There's one opposite by Cambridge University Press, and there's one just
There's the near one.
Okay, dropouts.
We will try to send an email to the current participants of
Okay.
both programs. Of both programs? I think so.
Okay, so let's say no speakers.